All right, so now we're going to move on to a new chapter. We are now going to talk about continuous groups. And this, of course, is getting into the heart of what a Lie group is, which we have not yet gotten to. We've discussed the classical groups, and we can certainly get a sense that the classical groups are going to have some kind of continuity because we know the classical groups are matrices. And, for example, the classical group, the general linear group in n dimensions over, say, R, clearly we know that we have n squared independent choices there, and those are all real numbers. So we choose a real number, we choose those n squared matrices. We've got an n squared matrix elements. We've got an element of the general linear group, but you can almost imagine that you take one of them, right, and you just make a little tweak, right? We add a little bit of a tweak to it, and so, or we subtract, and it's still a matrix. It's still a basis transformation that's applicable to some vector space V in n dimensions. And so certainly it's another element of this classical group. So clearly the number of elements in the classical group is clearly infinite. And the way I've just described it, it's clearly uncountable, right? It's not countably infinite, it's uncountable. So it's infinite and uncountable number of members of this group. And of course, we know it's a group because we have a group composition law, say, A dot B equals AB is another element of the group C. And every element has an inverse, right? A inverse A equals the identity. And of course, there is an identity. So we know this thing is a group. We know it's got an infinite, uncountable number of elements. So now, we could call that an infinite group, right? That's not a problem. The trick, though, is we have this word continuous group. So clearly, we have to understand the notion of continuity. And where does the notion of continuity come from? Where do we turn to understand continuity? The answer is topology, right? And like almost every physics/math book, Gilmore starts a crash course on topology. So he can define continuity. So he can define a continuous group. So he can ultimately define a Lie group. Now, I said in the prerequisites, you got to come here knowing some topology. And where do you get that? Well, you study it, right? There's a lot of ways of studying it. There's a lot of little crash courses on typology. I found those crash courses aren't so helpful because you kind of learn just enough to get yourself confused and in trouble. It's really something that's absolutely worth studying. Everybody should ultimately have some training in point set topology, right? You don't need to do algebraic topology. You don't need to do, fancy things about the fundamental group. Well, these aren't very fancy. These are also pretty elementary ideas. But the fundamental group is, if you start finding yourself studying, shapes and if you start finding yourself dealing with really, really abstract ideas, then that's a tough way of saying it too, because topology by its fundamental nature in its modern form is extremely abstract. The point is point set topology. Let's just put it this way. If you're bored to tears, you're studying the right thing, because point set topology is that absolute proof-driven, ultimately logic-driven, build it up from the axioms kind of thing, where everything is definition after definition after definition and proof after proof after proof. To get a good handle on starting this journey, you can go to my set of lectures called What is a Manifold? There I do a pretty good crash course on topology, but hopefully in conjunction with the book that'll get you somewhere. But we also cover what we're going to need in the next few lectures is this notion of a manifold. Okay, so what we're going to do today is we're going to talk a little bit about the notion of a continuous group and understand its continuity, but we're going to assume an elementary knowledge of foundational point set topology. This means that I'm expecting that everybody understands that if you take some set X, you can give that set a topology called a topology on X, and X plus in conjunction with its topology is called a topological space. And any element of the topology, remember the topology of X is the set of all open sets, right? So by definition, this is very definition driven. If you're an element of the topology, you are an open set. The topology is the collection of all open sets. And of course, a topology, in order for this to all make sense, there has to be some relationship between the open sets. And that, of course, is that infinite unions of open sets are open, finite intersections of open sets are open, the set itself is a member of the topology, and the null set is a member of the topology, right? So all those rules, which we're not going to go into here, right? We're not going to go into here, define what a topological space is. Another key point that you'll be expected to remember is that if you have a topological space X and a topological space Y, so I guess that would be X, Tx, Y, Ty, right? And you have a function from X to Y, f. That function is continuous if f inverse of an open set in Y, which I will say an open set in Y, if that is an element of the topology of X. In other words, the inverse of f maps open sets in Y to open sets in X. If that's the case, then f is continuous, right? F inverse may not be continuous, but f is continuous. In order for f inverse to be continuous, f itself, which is the inverse of f inverse, would have to map open sets from X to open sets in Y, right? And so that is that's how continuity is understood. So you see how you have to, in order to get to this idea of continuity through topology, you have to understand what is a topological space, how are topologies constructed on a topological space, and the definition of continuity is this strange thing where a function f is continuous from one topological space to another if its inverse maps open sets from the range space to open sets in the domain space. And the reason that this all boils down to the old epsilon delta proofs from calculus. This is an abstract statement of the epsilon delta proofs from calculus, but you definitely want to learn this abstract form, and it'd be great to understand. You really do want to understand how it connects to the epsilon delta form from standard calculus. But all of this is not what we're going to talk about today. I'm going to assume that you understand what continuity is. Okay, so let's begin and try to get at this idea of a continuous group. So we begin by defining the notion of a continuous group, and we start with the obvious fact that the continuous group is a set. Let's call this continuous group the set X. Now, it's not just a set, it's more than a set, but ultimately it is definitely a set. And it is a set that we are going to now endow with two critical structures. The first is a topological structure. In that topological structure, the core of any topological structure is it will be given a topology, but we can actually give it a little bit more because we're going to insist that this set is not only a topology, but it is also a manifold. And it is critical to understand what a manifold is. Before I said go back to this lecture, what is a manifold? That's part of the prerequisites of this course. And yes, in Gilmore's book, he does a crash course on manifolds. But that's exactly the kind of little mini crash course that shows up in these sorts of textbooks that is really, really unsatisfying. I encourage you to go through the lectures on what is a manifold before proceeding, because you really do want to understand it, because Lie groups are all about being manifolds. Now, you can probably make it without a total mastery of everything in the What is a Manifold lecture series. But look, this is it. I mean, Lie groups, which we're here to study, are continuous groups. To understand what a continuous group is, you have to understand that it has topological structure, right? That's part of the definition. What topological structure? Well, first of all, to say that it has topological structure and to assert that as a topology, that's really vacuous, because any topological structure must have a topology. So that's not very informative. But the fact that it has the topological structure of a manifold is absolutely critical. And look, to understand this, you've got to know what a manifold is. So we know that this set is now a manifold. So, well, all right, what does that mean? Well, here's my set X. I know it's a manifold, so I know it is, in this particular case, it's going to be, we're going to presume they're Hausdorff manifolds. We assume that its topology is Hausdorff, which means that any 2 points in the set can be put in their own open sets, and those 2 open sets will be disjoint, right? Or can be made disjoint. We know that's always possible for any 2 distinct members of the continuous group X. So we know that we've got a Hausdorff set, and we know that it's got the structure of a manifold. So how do we know what this means? Well, it means I can break this set up into subsets, open subsets, and each of those subsets can be mapped into the n-dimensional real space. So I can always map it to Rn. Each individual region in the underlying manifold or in the continuous group can be mapped into an n-dimensional real Cartesian space. And that mapping, I'll call phi, and I'll give it an index I, and each of these regions will be indexed by a number. I, maybe this is a different one, J, K, L. And each one of them can be mapped into its own n-dimensional real number space. So that means that I can take any point, right? I can take any point here and find a point here, and that mapping is an isomorphism, right? So I've got a 1-to-1 onto and invertible mapping that will take open sets in Rn and map them back to open sets over here, right? The inverse mapping, because it's 1-to-1 onto isomorphism and it's continuous, right? So that's what a manifold is. Now, the point is Rn, because, and we know this is doable because by definition, a continuous group must have this manifold structure. So it's a presumption that if you're a continuous group, you have this structure. Now, the point is that Rn, of course, is just a collection of n real numbers, right? And there's n of these. So each point here can be mapped onto a collection of real numbers, ordered collection of real numbers. And these real numbers here are called the coordinates. And what's important now is what I'm now saying is that every point in this set can be given coordinates through some mapping from a region around that point, which is called a chart, into Rn. I'm basically giving you this crash course in manifolds. But when we say something is a manifold, we're essentially saying we can give every member of the set coordinates. Right? Now, on top of that, this thing has to be a differentiable manifold. Well, actually, let's just say for now, it just has to be a manifold. So the topological structure of a continuous group is a manifold, which means every one of the points in the continuous group can be given coordinates. All right, so what else does it have to have besides topological structure? Well, it needs group structure. It needs the algebraic structure of a group. Well, what's the algebraic structure of a group? Well, that's really simple. If I have a member of the set X and I call it A, and I have another member of the set X and I call it B, then A, B must also be a member of the set, and A inverse must exist for every member A, and that equals the identity, and of course the identity must be in the group. And you have to have not commutative. It doesn't have to be commutative. Associativity, and it has to be associative. So all of the elements of this manifold, every point on this manifold must be able to algebraically combine with every other point via the algebraic structure of a group. Now, a normal manifold doesn't have that, right? A normal manifold is just a collection of points organized through a topology for which these maps into Rn are guaranteed to exist. These isomorphisms into Rn are guaranteed to exist locally around each point. By the way, each of these, you don't necessarily have to have one big map to one big map of Rn. In fact, you usually cannot. But X has to be able to be broken down into charts where these maps are possible. But just because you have a manifold, you certainly don't have a group structure. And it's also clear that a set with a group structure absolutely does not have to be a manifold. In fact, when you learn group theory, you learn discrete groups that aren't even infinite, right? And if the set isn't infinite, it's hard to give it the idea of being of a manifold topology. But so this is what a continuous group needs. It needs to have a topological structure, have a manifold, and the algebraic structure of a group. Oh, but wait. That's not all. These two structures must exist, but the structures need to be linked. The structures need to be linked together before you can actually have a true continuous group. So let's consider the set X. I'm going to make this box as the set X. And I consider one point in the set X, one element of this set, of this continuous group X. And then I consider another point in this continuous group over here. I know that a third point exists somewhere here that is the product of those 2 points, right? So if this is A and this is B, this is C, where A, B equals C. And here I've used the algebraic property. I've used the algebraic property between the elements of the set. Now, what's important to understand is that I can consider this as a function. And there's a lot of ways to do that. I can consider it as a function from X Cartesian product X. Oh, that's a mess, isn't it? X Cartesian product X back to X, right? That's the group operation, right? I guess I'll have to make my Cartesian product a little x. That's the group operation. It's a map from this is a set of all ordered pairs in of elements of the set X, and I'm mapping that set of all ordered pairs back into the set X, right? So to bind the algebraic and the topological properties, I have to ensure that the algebraic function that does this is continuous. Right? And the continuity merges the two together. I also have to make sure that the mapping from any element A, the mapping to its inverse, right, which is a mapping from the set X to the set X, but it's a special mapping, it's the inversion mapping, right? That also has to be continuous, right? So how does this look? So ultimately, this form of continuity is essentially saying that if I have A, B equals C, what I'm now going to say is that, if I take any element that's close to A, and by close to A, you mean in a neighborhood of A, which means in an open set containing A, and I take any element in an open set near B or around B, I'm going to get an element ultimately in an open set close to C, right? Now, we like to think of it generally the other way, which is if I take an element that's near C, I can find an element near A and near B whose product is this guy near C, right? And similarly, it is easy to show, well, not easy to show, but it's assumed. It's assumed because we're assuming the continuity. But the logic is the same. If I take A and I go out here to A inverse, then if I go to an open set around A inverse and I take the inversion of the inversion mapping, I'll get something near A, right? And that is what we mean by the group operation, right? The group operation is continuous under the topological structure of the continuous group, right? So the group is given a topology that's designed and assumed to make the algebraic structure continuous. That's this guy and this guy, these two operations. The operation of taking the inverse of something and the group operation, those have to be continuous operations or continuous functions under the topological structure of the group. So you can kind of see where this stuff becomes a bit confusing, right? Because you're merging two completely, really quite different branches of mathematics. It's actually kind of fascinating because when you study topology, you do not talk about groups. You do not. You talk about very abstract ideas like sets, and depending on how you approach topology, you might approach it from understanding real numbers, real analysis. Well, it's almost certainly you'll start from real analysis, and your first touch on topology is through real analysis. But then you'll take topology as an abstract class in and of itself. But group theory is a whole separate class, right? So merging these things together, that's the subject of Lie groups, right? That is this topic of Lie groups and Lie algebras. Ultimately comes down to having a topological space with a group structure laying on top of it, where the group operation is with the group operation and the group inverses and the inversion operation of the group are continuous under the topology of the group. That's really the core of what defines this subject. All right, so now let's see if we can organize our thoughts taking advantage of the fact that we have a manifold. Right now what we've done is we've taken advantage of the fact that we have a topology. Being a manifold has nothing to do with the continuity of these things, right? Being a manifold is an additional requirement that we have on top of this. You know, the fact that you can take the group and map it into real numbers and give everything coordinates is completely irrelevant to the question of whether the group operation and the idea of inversion mapping is continuous. That's all dependent entirely on what? On the topology of the group. The fact that it's a manifold now, we're going to take a little bit of advantage of that. All right, so now we're going to completely walk through the clean definition of a topological group as given by Gilmore. He calls them a topological group, also known as a continuous group. And number one, it is a manifold of eta dimensions. All right, that's the dimensionality we talked about here, right? These mappings are into an n-dimensional real space. So if you're a manifold, if you're an n-dimensional manifold, the dimension you're referring to is the dimensionality of the space you map into, right? And as we said in the last lecture, keeping track of the different things that have dimensions is really important. It turns out this dimensionality, I'll give you a hint, is actually the number of independent parameters ultimately in our isometry group. It is not the same as the dimensionality of the underlying vector spaces. We'll go through that whole thing at the end of this lecture. But the dimensionality of the manifold is this number right here. So the first thing you need is you need to be a manifold of n dimensions. Now, wrapped up in this manifold, by the way, are all of these different chart functions. I called them phi here, right? I'm going to change the name because I don't want to confuse, because Gilmore uses phi for different things. So we'll call them psi here. Well, unless, of course, Gilmore chooses to use psi soon. No, I don't think he does. So the chart mappings we'll call psi, right? Because Gilmore wants to use phi as the second big important thing a topological group must have, which is a map from two members of the manifold, say beta and alpha. Two members of the manifold beta and alpha have to go to another member of the manifold called gamma, right? So phi is so beta, alpha, and gamma are all members of the manifold. This, of course, is the group operation, right? But what we're doing is we're writing it in a slightly different notation. I'm going to write the group operation as phi beta alpha equals gamma, right? The other way to say it is beta alpha equals gamma. Sometimes you do beta group operation alpha equals gamma, but we're being a little bit formal here. So we're going to declare a mapping phi that takes beta alpha and gives gamma. And there's only one phi, right? There's only one phi. I just don't want you to confuse that phi with these chart mappings that define the manifold. So these are totally, now this is the part that's totally independent, right? The fact that you have a set that's a manifold of n dimensions, that's a set. And in that set are all these points. Two of those points, any two of those points, beta and alpha, we can combine using this other function, this group operation function, and get gamma. The next step is to look at these two things and realize, okay, we've got a manifold and we've got this group operation. Is there a way to sort of understand how I can use one to help me understand the other? Now, first of all, the fact that this is continuous is already part of the definition, right? This has to be a continuous operation, right? So that's behind us. The fact that this is continuous and the inverse operation is also continuous is behind us. I'm looking for something else now. I'm actually looking for how can I exploit these mappings, these mappings, these chart mappings, which force coordinates on every point. And the way I do that is I write this in coordinate form, which is pretty straightforward. I say B, well, B has coordinates, right? Or beta. It's going to have coordinate beta 1, beta 2, ... to beta n. That's the coordinate of beta. Alpha has coordinates also. Alpha 1, alpha 2, ... to alpha n. We know they have n coordinates because they are members of an eta dimensional manifold. Let me change this n to eta, an eta dimensional manifold. So it has eta dimensions. So I can write these points here as though they live in Rn, and the reason I can do it is because it's a manifold. So by definition, I have to be able to do it. So now that I know the coordinates of these 2 points, now that I have the coordinates of these 2 points, well, what about gamma? Well, gamma is going to have coordinates also, right? So we don't know how phi works necessarily, but we can definitely say something. We can say that we can say that the muth coordinate of gamma is definitely a function of the coordinates of the 2 points you're using to make gamma, right? So we know it's a function of that. Well, what do we want to call that function? Well, we want to call that function phi, but of course we're already using phi to refer to gamma in its entirety. So what we basically want is we want the muth projection of phi, right? So we only want the muth component of this thing, right? Because ultimately, this thing here, which equals gamma, it's going to equal gamma 1, gamma 2, ... gamma eta, but we only want gamma mu, right? So we're going to just take the muth component. We're going to treat this as though it's all of these together, but then when I add this superscript, I'm eliminating everything except the muth component, right? So that's how it looks. So the point I'm trying to get at is I'm going to say that the muth component of the answer of when you take the group operation between beta and alpha, that's some function phi superscript mu of the coordinates themselves, right? And the reason this is doable is because everything is an isomorphism. I know I have an isomorphism to this coordinate system. I know that I have an isomorphism to the coordinate system, so I can write beta and alpha isomorphically inside Rn. And because of the continuity of all of this, I know I have an isomorphism here. So now I just have to create these functions of these real numbers. These are all going to be real numbers because this is presumably a real manifold for now. In principle, I guess you could have a complex manifold, but let's just keep it simple. This is a real manifold. So I have a 2 eta function here, a function of 2 eta different variables, and it'll give me each component one by one. Well, I have eta functions, right? I have dimensionality eta, so I have eta functions, and each function has 2 eta variables, and from that I can construct the coordinates of any product of any 2 points in the manifold. Now this can be actually a little annoying to write down, so I might tend to write, as Gilmore does, I might tend to write the muth coordinate of gamma is phi mu, and then I just write beta and alpha, where it's implied that you're going to put the coordinates in there, right? This is a function, this guy here is a function of the coordinates of beta and alpha, but I only write beta and alpha because I don't want to write down beta 1, beta n, alpha 1, alpha n. So that's sort of a shorthand that's typically used. It's definitely used in Gilmore, but it's totally common. In general relativity, for example, you'll see coordinates, you'll see x. And x, of course, means all the points x0, x1. It means it's really the coordinates of the point x. Sometimes they'll write the shorthand x mu, and they'll intend it to mean that. Sometimes they'll use x mu just to mean one particular one, right? I've seen it done different ways. But okay, so we've got this shorthand out there. So now we can express all of the group properties in terms of this new notation. So this first statement, which we just worked on, that's closure, right? Because everything is inside the group, right? This is a group element, that's a group element, and these are the components of a group element when expressed in the coordinates. And this is all that shorthand we just did. We can also look at associativity, right? Associativity, which would be in abstract form, the element phi group. These circles represent the group operation, and beta and alpha you combine them through the group operation first, then with gamma, or gamma and beta first, and then with alpha. In our shorthand coordinate notation, we might write it this way: the coordinates of this algebraic product. It doesn't matter if you take gamma and combine it with phi operating on beta and alpha first, or if you take phi operating on gamma and beta first and then on alpha. Now notice, if you blow this up into the full inconvenient way, we might as well, just for illustration's sake, right? This is phi mu, and then this is gamma 1, gamma 2, gamma eta, maybe semicolon, and then this is phi 1, beta 1, beta eta, semicolon, alpha 1, alpha eta, close quote, and then comma phi 2, beta 1, beta eta, comma alpha 1, alpha eta, etc., all the way to phi eta, right? In other words, this, you can see how useful this shorthand is, right? Because we're using the abstract version inside the arguments here, But understand, the idea is this guy here is a function of real numbers, despite the fact you don't see the real numbers here. But what are those real numbers? Well, gamma has its eta coordinates because it's a manifold, right? That's the key of being a manifold, is I can take gamma and turn it into a string of real numbers through some sort of coordinate, some sort of coordinate structure, well, manifold structure on the underlying set. I can give it these coordinates. This guy here, right, well, that's just the algebraic product of beta and alpha, which previously we wrote like this. Unfortunately, we used gamma there too, but, you know, this is some other number here. Let's say it was pi, right? Pi mu, right? So this is just some other member of the space. Well, it can also be given coordinates. So it's got coordinates, it's got eta coordinates. The first coordinate, the second coordinate, the third coordinate, and each of those coordinates are functions of beta and alpha, which themselves can be given coordinates. So everything can be written in this massive coordinate language. And you can do this, this is what associativity looks like, but you can do it for identity and inverse. Okay, so where are we? So we started way back earlier lectures with an underlying vector space with n dimensions. So there's our first notion of dimensionality, n. That's a vector space over a field, and that field has dimensionality either 1, 2, or 4, right? So there's our second notion of dimensionality. Then the inner product, this inner product gave us some kind of isometry group. And that isometry group was a collection of n by n matrices, but we noticed that the amount of freedom, the degrees of freedom of those matrices was restricted. That was our previous lecture. So there's a restriction there. So we can call that the degrees of freedom in the isometry group. So that's yet another notion of dimensionality. Well, those degrees of freedom are ultimately going, this isometry group is a set that we are now going to give a manifold structure M, and the dimensionality of that manifold structure is going to be equal to the degrees of freedom. So the dimensionality of M equals the degrees of freedom inside that isometry group, right? So this can be now mapped into Rn, and we can give this isometry group essentially coordinates, right? So the isometry group gets basically turned into a manifold, and the dimensionality of the manifold is R. I guess I got to stick with it. I got to go R DOF. DOF is now representing the dimensionality of the isometry group, and then the isometry group, by being a group, also provides the group structure, and then the topology that we give this manifold and the group structure combine so that the group structure is continuous. Okay, and once we've done that, once we've taken our isometry group, established that it's a manifold whose dimensionality is the degrees of freedom. We did all that dimension counting in the last lecture so we could understand that. And we assert that the topological structure of the manifold will be such that the group operations and the inversion operation will be continuous. Now we have, that's where we are, right? We have yet to go back here, right? We have yet to go back here, because remember, the isometry group acts on this group, right? Every one of these matrices actually goes back and changes a basis here. But this guy's kind of fallen into the background a bit. Once we have this and this, that is going to start giving us what we need for our Lie group. But right now we're going to just call it a continuous or topological group, right? We're not using the word Lie yet, right? We're looking for the topological group or continuous group. Okay, so we'll press on in our next lecture.